Most people look at a massive industrial manufacturing floor and imagine greasy gears and heavy machinery, but the truth is that modern production is driven by microscopic precision and relentless digital orchestration. My name is Sarah, and I was the lead hardware automation engineer at a high-volume manufacturing facility, where my primary responsibility wasn't turning wrenches, but managing a massive, synchronized farm of hundreds of highly advanced Bambu Lab A1 printers. Coordinating an operation of that scale isn't just about pressing a print button. It requires orchestrating millions of lines of highly complex G-code simultaneously. Utilizing custom Python automation scripts that I developed and deployed directly from the Linux terminal on my ruggedized Chromebook. But my code didn't just tell the machines what to build. It was the critical digital safety barrier that kept the entire factory from literally burning to the ground. In hardware automation, the absolute most critical parameters are the thermal runaway protocols, the precise temperature limits of the extruders, and the maximum physical speeds of the stepper motors. If a machine pushes past its thermodynamic limits, the software must instantly cut the power, or the precision hardware will violently destroy itself. It was a flawless, mathematically tuned ecosystem designed to balance maximum output efficiency with absolute physical safety. But the greatest threat to a multi-million-dollar print farm isn't a mechanical failure. It is an arrogant executive who fundamentally believes that the immutable laws of physics and thermodynamics are just annoying software suggestions standing in the way of his quarterly production targets. Keep watching, hit that subscribe button, and welcome back to Scars and Silk. Today, I am going to show you exactly what happens when a toxic supply chain director forces you to bypass the thermal safety sensors in your Python code, and you simply step back and let the unyielding laws of physics completely melt his entire production floor to the ground. The disruption to our meticulously balanced production floor began the exact moment corporate brought in Marcus as the new director of supply chain. Marcus wasn't an engineer, and he certainly didn't understand the complex thermodynamic realities of operating a massive farm of Bambu Lab A1 printers. He was a pure logistics guy whose entire bonus structure was directly tied to ruthlessly accelerating our daily output volume. When he reviewed the analytics dashboard I had built to monitor the farm cycle times, he didn't see a perfectly optimized system operating at the exact threshold of peak physical safety. Instead, he saw what he completely misunderstood as intentional bottlenecks holding back the company's profit margins. He fundamentally could not grasp why the Python automation scripts I deployed from my Linux terminal enforced strict cooldown periods between heavy prints, or why the extruders were software locked to specific travel speeds. In his arrogant, numbers-obsessed mind, the carefully calculated G-code speed limits and the thermal runaway sensors weren't critical safety mechanisms preventing total hardware destruction. They were just overly conservative factory suggestions that were actively slowing down his production numbers. He looked at a beautifully orchestrated hardware ecosystem that was flawlessly churning out precision components 24 hours a day, and decided that my strict adherence to basic equipment safety was just a cowardly excuse for not pushing the machines twice as fast. Marcus officially summoned me into his office and handed down his absolute, non-negotiable mandate. He demanded an immediate 40% increase in our daily production velocity across the entire manufacturing floor. I calmly opened my ruggedized Chromebook, brought up the live Linux terminal, and tried to explain the completely unforgiving reality of hardware thermodynamics to a man who only understood spreadsheets. I explicitly told him that our massive fleet of Bambu Lab A1 printers was already operating at its absolute peak safe capacity, and that forcefully pushing the stepper motors and the extrusion hot ends any faster would require me to intentionally rewrite the Python automation scripts to actively bypass the built-in thermal runaway sensors. I clearly warned him that purposefully blinding our software to the hardware's live temperature telemetry wouldn't just result in a few warped prints, it would mathematically guarantee violent physical collisions along the kinetic axis and create an immediate, catastrophic risk of a severe thermal meltdown inside the extruders. Marcus simply scoffed at my warnings, aggressively accused me of being a rigid, technically inflexible engineer who cared more about babying the machinery than hitting our quarterly delivery targets, and gave me a direct, undeniable ultimatum to completely strip away the thermal safety protocols, ignore the terminal warnings, and violently overlock the entire facility's hardware by the end of the shift. I completely refused to waste my breath arguing against the fundamental laws of physics with a supply chain director who prioritized spreadsheets over basic thermodynamic reality. Instead, I calmly turned back to my Chromebook, opened a new document, and meticulously drafted a formal hardware destruction risk acknowledgment. I used explicit, mathematically undeniable language to document exactly what would happen when we bypassed the thermal telemetry, clearly stating that forcing the stepper motors beyond their physical limits and blinding the software to the extreme temperatures would guarantee violent axis collisions and create an immediate, catastrophic risk of internal component melting and localized fires across the entire print farm. I printed the document out, walked it directly into Marcus's office, and calmly informed him that I would not execute the reckless Python override script from my Linux terminal unless he formally signed his name, legally assuming absolute financial and operational responsibility for the mathematically guaranteed destruction of the hardware. Marcus actually laughed in my face, aggressively snatched the pen out of my hand, and called me a cowardly, overly protective engineer who was treating his heavy industrial output like a collection of fragile little toys. He arrogantly signed his name at the bottom of the page, fully convinced he was about to mastermind a record-breaking production quarter, and aggressively ordered me to execute the bypass immediately. So, I walked back to my terminal, completely disabled the thermal runaway sensors, and pushed his doomed, overclocked parameters directly to the entire fleet of Bambu Lab A1s. I want to pause the story right here to talk to every brilliant female engineer dealing with dangerously arrogant management. Have you ever had a toxic executive force you to push a system you knew with absolute certainty was going to physically destroy itself? Go down to the comments right now and drop a fire or a warning emoji if you know the absolute best defense against corporate greed is getting their reckless mandates signed in permanent ink. And make sure you hit that subscribe button to join the Scars and Silk Network, because you absolutely need to see exactly what happens when the unyielding laws of thermodynamics finally catch up to his overclocked production floor. Back to the story. Marcus got his reckless speed mandate, the executive board praised his aggressive new output strategy, and I sat back at my terminal, fully aware that we had just strapped a massive, ticking thermal time bomb directly to hundreds of high-precision machines. I opened my ruggedized Chromebook, brought up the live Linux terminal, and ruthlessly executed the modified Python override script, instantly broadcasting Marcus's highly aggressive, completely unhinged G-code parameters across the entire facility's network. In an instant, hundreds of Bambu Lab A1 printers simultaneously spun up to absolutely terrifying speeds, their stepper motors whining at frequencies they were never physically designed to sustain. For the first few hours, the sheer volume of output violently skyrocketed, and Marcus aggressively strutted across the manufacturing floor, loudly congratulating himself for single-handedly breaking the company's production records and mocking my previous technical warnings. But while he was busy celebrating his deeply flawed spreadsheet metrics, an invisible, mathematically inevitable disaster was rapidly brewing inside the hardware. Because the override script had explicitly blinded the system to all thermal telemetry, the software had absolutely no idea that the intense, relentless friction from the violently overlocked extrusion speeds was generating catastrophic levels of excess heat. The hot ends were desperately trying to push material significantly faster than the cooling fans could physically manage, and the internal temperatures of the extruders silently began to rise completely out of control. Without the critical thermal runaway protocols active to automatically sever the power, the machines were completely trapped in a violently escalating heat loop, blindly following their arrogant new orders as the unforgiving laws of thermodynamics quietly prepared to completely melt down his entire record-breaking production run. The inevitable physical disaster finally struck just after the mid-shift break, exactly as the immutable laws of thermodynamics dictated. Without the crucial safety limits to regulate the voltage, the heavily overlocked hot ends violently breached their maximum thermal thresholds, triggering a massive, synchronized thermal runaway event across the entire manufacturing floor. The intense, unregulated heat rapidly melted right through the protective silicone socks and instantly liquefied the internal PTFE tubing, causing the highly pressurized filament to aggressively boil and violently rupture directly out of the heat breaks. Because the Python override script had completely blinded the system to the catastrophic meltdown happening in real time, the automated software just kept relentlessly forcing the stepper motors to violently push the heavy, molten print heads across the kinetic axis at completely unsustainable speeds. The rapidly failing motors immediately began violently skipping steps, causing hundreds of heavy extrusion assemblies to lose their physical coordinates and violently crash into the glass print beds, slamming against the physical frame limits with a deafening, synchronized metallic crunch. In less than 20 minutes, the entire production floor was completely engulfed in a thick, toxic cloud of acrid black smoke and the deafening screech of emergency fire alarms, as Marcus stood completely paralyzed in the center of the room, helplessly watching millions of dollars of high-precision hardware literally melt itself down into useless, smoldering slag simply because he arrogantly thought he could outsmart the fundamental laws of physics with a corporate spreadsheet. With the entire manufacturing floor completely paralyzed and reeking of violently burnt plastic and twisted metal, Marcus desperately tried to save his job by loudly claiming to the emergency response team that there must have been a catastrophic bug in my Python automation scripts. I completely ignored his frantic, pathetic attempts to shift the blame, bypassed him entirely, and walked straight into the emergency crisis meeting that had just been convened with the facility's senior partners and the panicked executive board. I didn't utter a single word in my own defense. I simply connected my Chromebook to the main projector and illuminated the high-definition scan of the Hardware Destruction Risk Acknowledgment that Marcus had arrogantly signed just hours earlier. The massive screen perfectly highlighted his signature directly beneath the explicit, non-negotiable clauses detailing his absolute orders to violently bypass the thermal runaway sensors, ignore the terminal warnings, and systematically overclock the print farm into a mathematically guaranteed physical meltdown. It completely destroyed his desperate narrative about a software glitch, exposing the undeniable proof that his blind, arrogant obsession with spreadsheet metrics had intentionally triggered the massive industrial disaster. The entire executive boardroom went deathly silent as the reality of his gross operational negligence washed over the senior partners. Before the CEO could even fully process the devastating document, I calmly slid my company badge and a formal letter of resignation across the massive glass table, announcing that I was leaving the company effective immediately to launch my own elite hardware automation agency. However, because their entire manufacturing infrastructure was now completely destroyed and incapable of fulfilling a single order, I handed the senior partners a non-negotiable proposal for a $2.5 million emergency consulting fee to urgently rewrite the safety architecture and physically oversee the procurement and calibration of an entirely new industrial print farm. Marcus was instantly terminated for cause, publicly escorted off the smoldering production floor by corporate security, and the partners authorized my exorbitant consulting fee on the spot. I spent the next 8 months meticulously rebuilding the exact physical safety nets I had explicitly warned him not to destroy, entirely on my own terms and at exponentially more than my original salary. To every brilliant woman engineering the complex hardware of the modern industrial world, your true power isn't just in writing flawless automation code. It is in knowing exactly when to step back and let an arrogant executive physically melt down the machinery he refused to understand. If you know your worth in the hardware automation world, go down to the comments right now and drop a wrench or a robot face emoji so I know you are watching. And make sure you hit that subscribe button to join the Scars and Silk Empire. Protect your physical infrastructure, get every single catastrophic hardware mandate in writing, and never rebuild a melted print farm for free.